Hello, hello everyone. Welcome, dear aspirants and enthusiasts. Welcome to our physics family. Thank you for visiting our channel. So, today we will discuss a problem from TIFR 2020. Okay, so the problem basically says if you have a Lagrangian with generalized coordinate q1 and q2. So the Lagrangian is given here as this. So it contains q1 dot square, q2 dot square, and q1 and q2. So q1 and q2 are generalized coordinates. So where a and b are your constants. So in that scenario, you have to find the conserved quantity. Okay, so options are this. So sometimes it's very easy to find the cyclic coordinate in the Lagrangian, and accordingly you can find the conserved quantity, but sometimes it's not that much easy and you have to uh, change the coordinates, or you have to do the coordinate transformations so that you can find your cyclic coordinates, and from that you can find the conserved quantities. So here our Lagrangian is this, which contains q1 dot square, q2 dot square, and also q1 square, q2 square. So apparently this does not have any cyclic coordinate, but you can, if you can carefully observe the second term, here it contains q1 square and q1 square plus q2 square. So this term contains q1 square and q2 square and their summation. So if you try to transform it to polar coordinates, maybe there will be some term which does not contain the angular part. So let us have a try. So our Lagrangian was this. So let us choose a coordinate transformation so that your q1 becomes rho cos phi. So rho and phi are your new generalized coordinates. So similarly, you can transform q2 as rho sin phi. And what are the retransformation? So the retransformation will be rho square equals to q1 square plus q2 square, and your tan phi will be q2 by q1. So this set of four equations that will connect to generalized coordinates that have given in the problem with the two generalized coordinates that we have introduced here. So you can see the Lagrangian, it contains q1 dot square and q2 dot square. So let us do the derivative on q1 and q2. So first do it on q1. So you will get rho dot and rho phi dot. Your q1 dot will contain a term rho dot with another term rho phi dot with some cosine and sine coefficients. Similarly, you can calculate the derivative for q2, and this also contain the same rho dot and rho phi dot, but with different coefficient, with different trigonometric coefficients. Okay, so just look at the Lagrangian. Okay, and the coordinate transformation, you can see this one q1 and q2. So put the values of q1 q2 in the Lagrangian. So if you put that, the second term will take the values q1 and q2, whereas the first term q1 dot and q2 dot will take the values from the last equations. Okay, now again come to the point. So you have q1 and q2. So from q1 and q2 you can make the square quantities, and if you add them you will get rho square. So you can easily connect this term with the second term in the Lagrangian, which you can see here. So this is your second term in the Lagrangian, and it simply directly connects to this rho square. Okay, so immediately you can see that your Lagrangian now does not have any phi dependence in second term, but yet the first term have to be evaluated. So remember that your second term becomes rho square. Okay, so in next slide I will give you the value of rho 1 dot square and rho 2 dot square, and we will add them. So write down the rho 1 dot square. So it will contain rho dot square, rho phi dot square, and a term rho dot phi dot. So this will be the terms with some trigonometric coefficient. For example, rho dot square contains cos square phi and rho phi dot square contains sin square phi. Similarly, you can calculate rho 2 dot square and it will also contain rho dot square, rho square, phi dot square and rho dot phi dot. Okay, so there will be three terms in each with some trigonometric coefficients. But when you try to add these quantities q1 dot square and q2 dot square, if you try to add them, the third term will vanish. Okay, so the terms rho dot phi dot, they will cancel each other, and hence if you add rho 1 dot square and rho 2 dot square, you will simply get rho dot square and rho square phi dot square, and there will be no dependence of rho dot phi dot. Okay, so if you check that, you can find that rho dot square and rho 1 dot square plus rho 2 dot square does not contain any rho dot phi dot or any phi term. So again, rho 1 dot square plus rho 2 dot square does not contain any phi term. Okay, so come to the Lagrangian. So if you put the values of rho 1 dot square plus rho 2 dot square and rho 1 square plus rho 2 square, you will simply get this one, which does not contain any phi term. So this will be simply phi independent. And you know, if a Lagrangian does not contain any coordinate, any generalized coordinate, we call that generalized coordinate as cyclic coordinate. And essentially this will help us to find the conserved quantity. Okay, so come to the part. All of you know what is the Lagrange's equation of motion. So this is your Lagrange's equation of motion, where x is the generalized coordinate and x dot is generalized velocity, L is the Lagrangian. So if your Lagrangian does not contain any uh, coordinate, I mean if x is your generalized, sorry, if x is your cyclic coordinate, then this term del del x, that will be 0. Okay, so essentially that implies del x dot will be constant. Okay, so in our scenario the x was phi, so if you calculate del phi dot, that will give you a by 2 rho square, and derivative with respect to phi will give you 2 phi dot. So try to simplify it and you will get a rho square phi dot. So this is your conserved quantity. For the given Lagrangian, the conserved quantity is a rho square phi dot. But obviously we have to change this rho and phi in terms of q1 and q2. Okay, so again recall your coordinate transformations, and you know our tan phi was q2 by q1. So take the derivative so that you can get the value of phi dot. So if you take the derivative, your left hand side give you sec square phi dot, and right hand side obviously give you rho 1 rho 2 dot minus sorry, q1 q2 dot minus q2 q1 dot divided by q1 square. So now phi dot will be obviously this term which contains q1 q2 and a term cos square phi. So plug this phi dot into the del phi dot, then you will get simply this one. Now you can see that our rho square cos square phi was q1 square, because we have defined the q in that way. So q1 was rho cos phi. So you can simply cancel these two terms. Okay. So now your del phi dot becomes a q1 q2 dot minus q2 q1 dot. So this will be your conserved quantity. Okay, so what is our take home message? So remember that it's not too much obvious that a Lagrangian contains any cyclic coordinate or not. So sometimes you have to do the coordinate transformation so that you can find the symmetry in the Lagrangian or the symmetry of the system. Okay, thank you.